Now in this lecture we will find out the radius of the circle using two different methods. In the drawing we have this circle. We know that the center of this circle is at this point, point O. We also know that line segment AB equals to 6 units in its length. Line segment AD equals to 18 units. Line segment BC equals to 13 units. Angle BAC, this angle equals to 90 degrees. Angle ABC, this angle equals to 90 degrees. And our mission is to find out the radius of this circle. So first of all, we'll make a construction from point C. This is to say, from this point, we will draw perpendicular on AD. This is AD. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. In the next step, we will define the touching point of the perpendicular from point C and AD as E. Actually, we created here quadrilateral ABEC. This quadrilateral ABEC has 1, 2, 3 right angles. The sum of 3 right angles is 90 times 3, 270 degrees, plus the missing side, the missing angle here. In total, they must be equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So because of the fact that this quadrilateral ABEC has 4 right angles, therefore quadrilateral ABEC must be at least a rectangle if not a square. So we relate to this quadrilateral ABEC as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say AB equals to EC. AB equals to EC. But we know that AB equals to 6 units, therefore EC also equals to 6 units. According to the sum rule that the opposite sides of a rectangle are equal to each other, it means that BC equals to AE. So BC equals to 13, therefore AE equals to 13 units also. And what is the length of line segment ED? The length of this line segment ED will be equal to AD minus AE. Again, AD minus AE equals to ED. That is to say, ED equals to AD, that is 18 units, minus AE, that is 13 units. 18 minus 13 is 5, so ED equals to 5 units. In the next step, we'll join points D and C together by a straight line. By joining points D and C, we created here the right small triangle CED. We'll implement the Pythagoras theorem on this right small triangle CED. The right small triangle CED, this right triangle, by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this, small right triangle ECD equals to DC. Therefore, the square of the hypotenuse is DC squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC squared plus ED squared. In conclusion, according to the Pythagoras theorem, we get that in the right triangle CED, DC squared equals to EC squared plus ED squared. DC squared, that is the square of the hypotenuse, must be equal to EC squared EC equals to 6, therefore EC square will be equal to 6 squared, that is 36, plus ED squared. ED equals to 5, therefore ED squared is 5 squared, that is 25. In conclusion, we found out that DC squared equals to 36 plus 25. That is to say, DC squared equals to 36 plus 25 is 61. Here we'll take a root out of this equation and we'll get that DC equals to the square root of 61. So we found out that the hypotenuse of DC here is equal to the square root of 61. In the next step, we will join points B and D together by a straight line. By joining points B and D, we actually created the right triangle ABD. So we actually will implement the Pythagoras theorem on the right triangle ABD. On the right triangle ABD, by PT is the version for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle ABD, this right triangle, the hypotenuse is BD. Therefore, the square of the hypotenuse is BD squared. And it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to AB squared plus AD squared. So BD squared equals to AB squared plus AD squared. So BD squared, that is the square of the hypotenuse in the right triangle ABD, equals to AB squared. Here AB equals to 6. Therefore, AB squared equals to 6 squared, that is 36, plus AD squared. Here, AD equals to 18 units, according to what is given as the question. Therefore, AD squared equals to 18 squared, that is 324. So, in conclusion, we found out that BD squared, the square of the hypotenuse, equals to 36 plus 324 is 360. So, BD squared equals to 360. Here we'll take a root out of this equation and we'll get that the square root that BD square equals to 360. So if we take a root out of this equation, we get that BD equals to the square root of 360. So BD equals to the square root of 360 is 36 times 10. We will take 36 out of this root. The square root of 36 is 6. So BD equals to 6 times square root of 10. So we found out that the hypotenuse BD equals to 6 times square root of 10 units. In the next step, we'll find out the area of triangle BDC. Here we'll find out the area of this green triangle, triangle BDC. The area of the green triangle BDC here, the square brackets is the same for the area. So the area of the triangle, green triangle BDC, will be equal to the base of the triangle times the height to the base over 2. You should remember that the height to the base must create 90 degrees with the base. So the area of the green triangle BDC will be equal to the base. The area of the green triangle BDC equals to the base. We will choose the base as BC. So the base equals to BC times the height. Again, the height must create 90 degrees with the base BC. So B is on BC, C is also on BC. So we will take the vertex D of the green triangle BDC, and from the vertex D we will raise the midpoint perpendicular on the extended BC. We'll extend BC by a straight line, and then from point D, that is the vertex of the green triangle DBC, we'll draw perpendicular on the extended BC. So here this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D on the extended BC as point F. So here, because of the fact that DF creates 90 degrees with the extended BC, it means that DF is the height to the base BC. Okay? Now we'll find out the value of the height DF. We'll focus on quadrilateral ABDF. In quadrilateral ABDF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the fourth angle must be equal to 360 degrees. Therefore, the fourth angle must be equal to 90 degrees in order to complete the sum of the angles in quadrilateral ABDF to 360 degrees. This angle must be equal to 90 degrees. And because of the fact that angle ADF, this angle equals to 90 degrees, it means that quadrilateral AB, quadrilateral ABDF has 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle. So we will relate to quadrilateral ABDF as a rectangle. Is a rectangle. Quadrilateral ABDF is a rectangle, but we also know that the opposite sides of a rectangle ABDF must be equal to each other. That is to say, AB equals to DF. AB equals to DF. I'll write it down. According to the rule that the opposite sides of rectangle ABDF must be equal to each other, we'll get that AB equals to DF. But it is given us the question that AB equals to 6 units. We can write here that AB equals to 6, and from this equation 6 equals to AB equals to DF, we will derive that DF is also equals to 6 units. Here DF equals to 6 units. That is to say, the height to the base BC is equals to 6 units. So, according to our formula, the area of the green triangle BDC, the area, as you can see here, it is equal to the base times the height over 2. And the base is BC times the height, that is 6 over 2. So the area of the green triangle BDC equals to BC times 6 over 2. But we know that BC equals to 13. So we substitute BC by 13. That is the base times the height, that is 6 over 2. 6 over 2 is 3. So in total this expression equals to 6 over 2 is 3. So in total, this expression equals to 3 times 13, that is 39. That is to say, the area of the green triangle BDC equals to 39 square units. So we found out that the area of the green triangle BDC equals to 39 square units. In the next step, I will present to you a new rule, and we'll implement the new rule in our drawing. Okay, so the new rule is rule number 1. According to rule number 1, if a triangle is blocked by a circle, so first of all I will draw the rule number 1 here. So we have first of all this circle. The center of the circle is here. In this circle we have triangle ABC that is blocked by this circle. This is triangle ABC, and actually triangle ABC is blocked by this circle. Triangle ABC is blocked by this circle. The center of this circle is at point O. And we know that the length of side AB of triangle ABC is equal to A units, side BC equals to B units in its length, and side AC equals to C units in its length. And the radius of this circle, that is to say OM, we'll define the radius of this circle as capital R. So according to rule number 1, if a triangle, for example triangle ABC, is blocked by this circle, then the radius of this circle that blocks triangle ABC, that is to say capital R, will be equal to the multiplication of the side lengths of the triangle ABC by each other, that is to say A times B times C, over 4 times the area of triangle ABC that is blocked by the circle. 4 times the area of triangle ABC. Okay? So I repeat again, if we have this circle and we have a triangle ABC that is blocked by this circle, what is the definition of a triangle that is blocked by a circle? It means that all the 3 vertices of this triangle, that is to say those 3 vertices touching the circle. This vertex starts the circle at point A, this vertex starts the circle at point B, and this vertex of the triangle touches the circle at point C. If not all the 3 vertices touching the circle, if we have only 2 vertices that's touching the circle, it is not defined as a triangle that is blocked by the circle. In order that a triangle will be blocked by a circle, all three vertices, like in this drawing, must touch the circle. So you can see here. So here we have triangle ABC that is blocked by this circle, and the length of side AB is A units, the length of side BC is B units, and the length of side AC is C units, and the radius of this circle OM equals to capital R. Then the value of the radius capital R will be equal to the multiplication of the side lengths of the triangle, that is to say A times B times C, over 4 times the area of this triangle, triangle ABC, that is blocked by this circle. Okay? Now we can implement this rule number 1 in our drawing. Why? Because of the fact that in our drawing we have this circle. In our drawing, this circle blocks triangle BCD. I'll write it down. The green triangle, triangle BCD, is blocked by the circle So you can see that the vertex here is blocked by, touches the circle at point B. The vertex here touches the circle at point C, and the vertex here it touches the circle at point D. Therefore, the definition of rule number 1 of a triangle that is blocked by a circle is satisfied by this drawing, because we have all the vertices of the green triangle are touching the circle at different points, at points B, C, and D. Therefore, we can implement here rule number 1. And according to rule number 1, the radius of this circle, so we will define the radius of this circle here, OM, as capital R. According to rule number 1, capital R, that is the radius of this circle. I'll repeat again. In our original drawing, the green triangle BCD is blocked by the circle. Why? Because all the 3 vertices of the triangle are touching the circle at different points. Therefore, it is indeed blocked by the circle. Therefore, according to rule number 1, the following equation is true, that the radius of this circle that is equal to capital R will be equal to the multiplication of the side lengths of the triangle by each other. The length of side BC is BC times the length of side DC, that is DC, times the length of side BD, that is BD, over 4 times the area of the green triangle, triangle BCD. Okay? So the radius that we are looking for of this circle, that is to say capital R, will be equal to BC. BC equals to 13 units in its length, so we'll substitute BC by 13 times DC. DC equals to the square root of 61. So we substitute DC by the square root of 61 times BD. The length of BD is equal to 6 times square root of 10 units. So we substitute BD by 6 times square root of 10 units. over 4 times the area of the green triangle BCD. We have already found out that the area of the green triangle BCD equals to 39 square units. So we substitute the area by 39 square units. Okay, in conclusion, we found out that the radius that we are looking for of this circle will be equal to 13 times square root of 61 times 6 times square root of 10 over 4 times 39. Here we will divide both the numerator and the denominator of this expression by 13. So here we have 13 in the numerator, so 13 over 13 is 1. So 13 will get cancelled. In the denominator we have 4 times 39. So 39 over 13 is 3. Okay, so we'll cancel the 39 and we'll write down instead of 39, 3. So in conclusion, we found out that the radius of the circle that we are looking for it is equal to square root of 61 times square root of 10 times 6 over 4 times 3 is 12. Here we will divide both the numerator and denominator of this expression by 6 and we'll get that the radius that we are looking for, that is to say the radius of this circle, it is equal to the square root of 61 times square root of 10 times 6 over 12. So we will divide the numerator by 6. So 6 over 6 is 1, so 6 will get cancelled. And we will divide the denominator by 6. In the denominator we have 12. 12 over 6 is 2, so we'll cancel 12 and write down 2 instead of 12. So in conclusion, we found out that the radius of the circle that we are looking for, the radius of this circle, that is to say capital R, it is equal to the square root of 61 times the square root of 10 over 2. According to the algebraic identity, that the square root of A times square root of B equals to the square root of A times square root of B equals to the square root of A times B. We will get that the square root of 61 times the square root of 10 equals to the square root of 61 times 10 over 2. 61 times 10 is 610. So in the square root we have 610 over 2. So we found out that the radius of this circle, the radius that we are looking for, that is to say capital R, is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay. So we finished with the first method. In the next step, I will present to you the second method. I will not repeat on the same things that we have already done in the first method. In order to shorten the lecture. So here from point C we go perpendicular on AD. This angle equals to 90 degrees. This angle equals to 90 degrees. We define the touching point of the perpendicular from point C and AD is E. We have already found out that EC equals to, actually AB, EC, it is a rectangle, and the opposite sides of a rectangle are equal to each other. Therefore, if AB equals to 6, then EC equals also to 6, and EA equals to 13 units according to the same rule that the opposite sides of a rectangle are equal to each other. We have already found out that ED equals to AD minus AE, that is to say ED equals to 5 units. Point O is the center of this circle. From point O, we'll draw perpendicular on chord BC. So the next construction is that from point O, that is the center of the circle, we will draw perpendicular on chord BC. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point O and BC as N, or capital N. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. According to the new rule that we will define as rule number 2, it is, rule number 2 is true in any circle. So if we have this circle, could be actually any circle. The center of the circle is at this point, and here we actually have here chord BC, could be any chord. This is chord BC, that could be any chord. Point O, this point is the center of the circle. So actually from the center of the circle, that is to say from point O, we will draw perpendicular on BC. So according to our construction, this angle equals to 90 degrees, and this angle, it is also equal to 90 degrees. We'll define the touching point of the perpendicular from point O and BC as E. And according to this rule number 2, the perpendicular from point O on chord BC bisects chord BC. That is to say, according to rule number 2, if BC has been bisected by OE, it means that BE is equal to EC. Okay? So whenever you draw perpendicular from the center of the circle to any chord, it bisects the chord. That is to say, in this case, chord BC has been bisected. It means that BE equals to EC. Okay? So actually we can implement rule number 2 in our drawing. Why? Because in our drawing, from point O, that is the center of this circle, we drew perpendicular on chord BC. It is perpendicular because this angle equals 90 degrees and this angle equals 90 degrees, according to our construction. So ON bisects BC according to rule number 2. So I write it down. BN equals to NC BM equals to NC according to the new rule, rule number 2. BN equals to NC. We will define the touching point of the perpendicular from point O and AE as M. So we will focus on quadrilateral ABAM, ABMN, this quadrilateral, the upper quadrilateral ABMN. In quadrilateral ABMN, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. This angle equals to 90 degrees. And because of the fact that in quadrilateral ABMN we have 4 right angles, therefore quadrilateral ABMN must be at least a rectangle if not a square. So we will relate to quadrilateral ABMN as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle ABMN, its opposite sides, they are equal to each other. That is to say, AM equals to BN. AM equals to BN. In the next step, we will focus on quadrilateral, the lower quadrilateral MNEC. This quadrilateral MNEC. In the quadrilateral MNEC, we have 1, 2, 3 right angles. So I write it down. Quadrilateral MNEC. So in quadrilateral MNEC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be equal to 90 degrees. This angle must be equal to 90 degrees. And because of the fact that in quadrilateral MNEC we have 4 right angles, quadrilateral MNEC is a rectangle. Again, we know that the opposite sides of a rectangle are equal to each other. The opposite sides of rectangle MNEC are equal to each other. That is to say, ME equals to NC. ME equals to NC. So we can summarize what we have already found out until now. We have already found out that according to rule number 2, BN equals to NC. But we also know, we have already also found out that Bn itself, it is equal also to Am. So we can write here that Bn equals to Am. And we have already found out that Nc, it is also equals to Me. So we can write here that Nc equals to Me. So we have here a long equation, and from this equation Am equals to Bn equals to Nc equals to Me, we will derive that Am equals to Me. Am equals to Me. Okay. So here, side Am, this side Am equals to side Me. Okay. In the next step, we will extend line segment AD by a straight line towards the upper side of the circle until it touches the circle. We'll define the touching point of the extended line segment AD and the circle as point F. By extending line segment AD, we created here chord FD. We created here chord FD. And we already made the construction of perpendicular ON on BC. Because of the fact that ON is perpendicular, it is absolutely a straight line. So ON is perpendicular, therefore it is a straight line. So if you focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule number 1, that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees according to the rule that I mentioned. Therefore the missing angle must be also equal to 90 degrees, because in total the sum of those two angles must be equal to 180 degrees. Likewise, if you focus on the lower side of the straight line ON at point M, here according to the same rule, in the lower side of the straight line ON, the sum of the angles must be equal to 180 degrees. So which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees according to the same rule. Therefore the missing angle must be equal to 180 degrees. In order to complete the sum of the angles on the lower side of the straight line ON at point M to 180 degrees, the missing angle must be equal to 90 degrees. So we actually found out that OM is perpendicular to FD. Why OM is perpendicular to FD? Because of the fact that this angle equals to 90 degrees and this angle equals to 90 degrees. So I can write down that OM, the line segment that exits from the center of the circle, OM is perpendicular to chord FD. And because of the fact that OM is perpendicular to FD, we can implement here rule number 2. Okay? Whenever we have from the center of the circle perpendicular to any chord, we can implement rule number 2. According to rule number 2, the perpendicular OM from the center of the circle bisects chord FD. That is to say, FM equals to MD. FM equals to FD according to rule number 2. Okay? FM equals to MD. Why? Because OM bisects chord FD. That is to say, it cuts it into two halves. This half equals to this half. FM equals to MD. What is the value of FM according to this drawing? FM equals to FA plus AM. FA plus AM. And it is equal to FD. It is equal to FM equals to MD. FM equals to MD. OM bisects FD. It means that FM equals to MD. FM equals here to MD. Not FD but MD again. FM equals to MD. So what is the value of MD? MD, from the drawing it is very easy to see that MD equals to ME plus ED. ME plus ED. So FM equals to MD means that FA plus AM equals to ME plus ED. But we have already found out that AM equals to ME. AM equals to ME. So here AM equals to ME, therefore we can cancel those two line segments because they are equal to each other. And we left only with FA that is equal to ED. So we found out that FA equals to ED. FA equals to ED. But we have already found out that ED equals to 5 units. So from this equation FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. FA equals to 5 units. Okay. In the next step, we will extend line segment BA until it touches the circle. At this point, we will define the touching point of the extended line segment BA and the circle is point P. I've already presented to you this rule. We call this rule number 2. Let's have another rule number 2 here. So according to the old rule number 2, it is true in any circle. If chord AB intersects with chord CD at point O, point O is the intersection point between the two chords, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, so we can actually implement rule number 2 in our drawing. Why? Because in our drawing we have chord FD. This is chord FD that intersects with chord PB at point A. I'll write it down. In our original drawing we have chord FD that intersects with chord PB. This is chord PB at point A. The intersection point between the two chords occurs at point A. Therefore, according to the old new rule 2, we will get that FA times AD, FA times AD will be equal to PA times AB. I'll repeat again on rule number 2. FA times AD equals to PA times AB. Again, because of the fact that chord FD intersects with chord PB at point A, according to the old new rule, the old rule number 2, FA times AD equals to PA times AB. FA equals to 5, AD equals to 18. PA is the missing line segment, so we will leave it as it is. Times AB, AB equals to 6, so we substitute AB by 6. In conclusion, we found out that according to the old rule number 2, FA times AD equals to PA times AB. we will divide this equation by 6 and we get that the missing line segment PA equals to 5 times 18 over 6. Here 18 over 6 is 3 and 3 times 5 is 15. So we found out that PA equals to 15 units. Here we can write down that PA equals to 15 units. So in the next step I will present to you a new rule that will be rule number 4, and we will implement the new rule in our drawing. Okay, according to the new rule, so first of all I will draw the circle. If chord AB, this is called AB. Intersects with chord CD, this is called CD. At 90 degrees. That is to say, they create between them, the two chords create between them 90 degrees. So this angle equals to 90 degrees. And the intersection point occurs at point O. So I write it down, rule number 4. If chord AB, this is chord AB, intersects with chord CD, this is called CD, at 90 degrees. They create between them at the intersection point 90 degrees, as you can see here. And the intersection point occurs at point O. So if this is the data that has been given to us, then we can implement here rule number 4. And according to rule number 4, if the radius of this circle equals to capital R, that is to say here always this point E is the center of the circle, point M is the point of the circle itself, therefore EM is the radius of the circle that we will define as capital R. So according to, so if this is the data that has been given to us, then for R square, R is the radius of the circle, will be equal to AO square plus OB square plus CO square plus OD square. I'll repeat again, if chord AB intersects with chord CD at 90 degrees at point O, then the following equation is true, that 4R square, R is the radius of the circle, will be equal to AO square plus OB square plus CO square plus OD square. So actually can implement rule number 4 in our drawing. Why? Because in our drawing we have chord FD, this is called FD, intersects with chord PB, this is called PB, at 90 degrees. That is to say, at the intersection point, they create between them 90 degrees. and the intersection point is at point A. I'll repeat again. In our original drawing, we have chord FD that intersects with chord PB at 90 degrees. At point A. Therefore, we can implement here rule number 4. According to rule number 4, if we define the radius of this circle as capital R, here OM, that is the radius of this circle, will be equal to capital R according to our definition. We will get that 4R squared. R, capital R is the radius of the circle, so I already mentioned. 4R squared equals to FA squared plus AD squared plus PA squared plus AB squared. I'll repeat again. Because of the fact that chord FD intersects with chord PB at 90 degrees at point A, we'll get that according to rule number 4, 4R squared, R is the radius, capital R is the radius of the circle. 4R squared equals to FA squared plus AD squared plus PA squared plus AB squared. So 4R squared equals to FA squared. FA equals to 5, therefore FA squared equals to 5 squared, that is 25, plus AD squared. AD equals to 18, therefore AD squared equals to 18 squared, that is 324, plus PA squared. PA equals to 15, therefore PA squared equals to 15 squared, that is 225, plus AB squared. AB equals to 6, therefore AB squared equals to 6 squared, that is 36. In conclusion, found out that 4R squared equals to 25 plus 225 is 250, and 324 plus 36 is 360. So we found out that 4R squared equals to 250 plus 360 equals to 610. 4R squared equals to 610. We'll divide this equation by 4 and we'll get that R squared equals to 610 over 4. Here we'll take a root out of this equation and we'll get that R equals to the square root of 610 over 4. So we have here the square root of 610 and the square root of 4 is 2. So we can take out 4 out of the root. We can take 4 out of the root, and instead of 4 we'll find out 2. So we actually found out that the radius of the circle that we are looking for, the radius of this circle capital R, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it equals to 12.349 units. I repeat again. The radius of this circle equals to either the square root of 610 over 2, or in terms of numbers, it is equal to 12.349 units. So we finished with the second method. In the next step, I will summarize the lecture. We'll start with the first method. So in the drawing we have a circle. Inside, we know that the center of the circle is at this point, point O, and we know that line segment AB equals to 6 units in its length. Line segment AD equals to 13 units in its length, and line segment BF equals to 13 units. Angle DAB, this angle equals to 90 degrees, that angle ABC equals to 90 degrees. Our mission is to find out the radius of this circle. Here we know that the radius of this circle equals to OM, that is equal to capital R according to our definition. So first of all, we made the construction. From point C, we drew perpendicular on AD. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We defined the touching point of the perpendicular from point C and A, this E. So here, we created quadrilateral ABEC. In this quadrilateral ABEC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And because of the fact that quadrilateral ABEC has 4 right angles, it means that quadrilateral ABEC is a rectangle. That is a rectangle, if not a square, so we will relate it as a rectangle. We will relate to quadrilateral ABEC as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC. But AB equals to 6 units according to what is given as the question. Therefore, EC must be also equal to 6 units. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we will get that BC equals to AE. But BC equals to 13 units according to what is given as in the question. Therefore, AE must be also equals to 13. What is the length of ED? ED equals to AD minus AE. AD equals to 18 units, AE equals to 13 units. Therefore, AD minus AE is 18 minus 13, that is 5. That is to say, we found out that ED equals to 5 units in its length. Then, we actually connected points D and C together by a straight line. In this way, we created the small right triangle DC. We created here triangle DC. We created here triangle CDE, this small right triangle CDE. Okay, so we can implement the Pythagoras theorem on the small right triangle CDE. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse must be equal to the sum of the squares of the perpendicular. So in the right triangle CD by PT is abbreviation for Pythagoras theorem. The hypotenuse is CD, therefore the square of the hypotenuse is DC square, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to EC square plus ED square. So in conclusion, we found out that DC square equals to EC square plus ED square, according to the Pythagoras theorem. So DC square equals to EC square. EC equals to 6, so EC square equals to 6 square, that is 36, plus ED square. ED equals to 5 units, therefore ED square equals to 5 square, that is 25. So in conclusion, we found out that DC square equals to 36 plus 25. 36 plus 25 is 61. So in conclusion, we found out that DC square equals to 61. We took a root out of this equation and found out that DC equals to the square root of 16 units. So the hypotenuse DC here equals to the square root of 61 units. Okay, in the next step, we connected the joint points B and D together by a straight line, and we implemented the Pythagoras theorem on the right triangle ABD. In the right triangle ABD by PT, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is BD, therefore the square of the hypotenuse is BD square. and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AB square plus AD square. Here, BD square must be equal to AB square plus AD square. So BD square that is the square of the hypotenuse, must be equal to AB square. AB equals to 6, therefore AB square equals to 6 squared, that is 36, plus AD square. AD equals to 18 units, therefore AD square equals to 18 squared, that is 324. So in conclusion, we found out that BD square, that is the square of the hypotenuse in the right triangle ABD, equals to 36 plus 324. 36 plus 324 equals to 360. So in conclusion, we found out that BD square equals to 36 plus 324 is 360. BD square equals to 360. We took a root out of this equation and we found out that BD equals to the square root of 360, but 360 equals to 36 times 10, so we substitute 360 by 36 times 10. So the square root of 36 times 10, we can actually take out 36 out of the root. Why? Because of the fact that the square root of 36 is 6. Okay, so we took 36 out of the root and we got here 6. Inside the root we left only the square root of 10. Therefore, we actually found out that the hypotenuse BD in the right triangle ABD equals to 6 times square root of 10 units. Here, the hypotenuse BD equals to 6 times square root of 10 units. Okay, in the next step, we calculated the area of the main triangle BDC. The area of any triangle in the space and also of triangle BDC, it is equal to the base of the triangle times the height to the base over 2. I must emphasize that the height to the base must create 90 degrees with the base. So the area of any triangle, it is equal to the base times the height to the base over 2. And the area of triangle BDC equals to the base of the triangle. We choose the base of the triangle as BC. So we substitute the base by BC times the height over 2. What is the height of the main triangle BDC? Here, point B is on BC, therefore we cannot draw the height from point B, and point C is also on BC itself, so we can not draw the height from point C. But here we have the vertex D that is not on BC, therefore we can draw the height to the base that must be perpendicular to the base of the extended base. So we extended BC by a straight line, and then from point D, that is the vertex of the green triangle BCD, we actually drew perpendicular on the extended BC. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point D on the extended BC as F. Actually, in this way, we created quadrilateral ABDF. Inside quadrilateral ABDF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be equal to 90 degrees. And because of the fact that in quadrilateral ABDF, we have 4 right angles, therefore quadrilateral ABDF is a rectangle. Okay? Here, quadrilateral ABDF is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to DF. AB equals to DF. AB equals to DF. But it is given us the question that AB equals to 6 units. So we can write here that AB equals to 6, and from this equation 6 equals to AB equals to DF, we will derive that DF is also equals to 6 units. Here df, that is the height to the base BC, equals to 6 units. Now we can calculate the area of the green triangle BDF because we got the value of the height. Okay, so the area of the green triangle BDC, the square brackets is the same for the area, will be equal to the base, and the base is BC, and BC equals to 13, so we substituted the base by 13 times the height. We found out that the height equals to 6 units, so we substituted the height by 6, so it is 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. So in conclusion, we found out that the area of the green triangle BDC equals to 39 square units. Okay, the area of this green triangle equals to 39 square units. Then I presented to you rule number 1, and we implemented rule number 1 in our drawing. According to rule number 1, if we have this circle, inside this circle we have triangle ABC. This is triangle ABC. Side AB equals to A units, side AC equals to C units in its length, and side BC equals to B units in its length. And the center of this circle is point O, and the radius of this circle equals to capital R according to our definition. So if we have a triangle that is blocked by a circle, like in our drawing, then the radius of this circle, that is to say capital R, will be equal to A times B times C, that is the multiplication of the side lengths of triangle ABC by each other, over 4 times the area of this triangle, triangle ABC. What is the definition of triangle that is blocked by a circle? A triangle can be blocked by a circle only and only if all the 3 vertices of the triangle touches the circle at different points. Like here. This vertex touches the circle at point C, this vertex touches the circle at point B, and this vertex touches the circle at point A. Only if all the vertices of the triangle touches the circle at different points, only then we can say that the triangle is blocked by a circle, like in this drawing. Okay, so the radius of this circle equals to A times B times C over 4 times the area of this triangle, triangle ABC, that is blocked by a circle. So we actually can implement rule number 1 in our drawing. Why? Because in our drawing we have the green triangle, triangle BCD. This triangle BCD is blocked by this circle. Why? Because of the fact that this vertex touches the circle at point B, this vertex touches the circle at point C, and this vertex touches the circle at point D. Therefore, we can say for sure that the green triangle is blocked by the circle, and therefore we can implement here rule number 1. I'll repeat again, the green triangle BCD is blocked by the circle, and therefore, according to rule number 1, we will get that the radius of this circle, we define the radius of this circle as capital R, because OM is the radius of the circle, and we define it as capital R. The radius of this circle will be equal to the multiplication of the length sides of the triangle, that is to say BC times CD times BD, BC times DC times BD, over 4 times the area of this triangle that is blocked by the circle, over 4 times the area of triangle BCD. The square bracket is the same for the area of triangle BCD. BC equals to 13 units in its length, CD equals to a square root of 61 units in its length, and BD equals to 6 times square root of 10 units in its length. So we wrote down the values of the sides over 4 times the area of triangle BCD. We already found out that the area of the green triangle BCD equals to 39 square units. So in conclusion, we found out that the radius of this circle that blocks the green triangle BCD equals to 13 times square root of 61 times 6 times square root of 10 over 39 times 4. Here we divided both the numerator and the denominator of this expression by 13. So in the numerator we have 13 over 13 is 1, so 13 will get cancelled. In the denominator we have 4 times 39. And 39 over 13 is 3. So we cancelled 39 and we wrote instead 39 3. So in conclusion, we found out that the radius of this circle that blocks the green triangle BCD equals to the square root of 61 times square root of 10 times 6 over 3 times 4 is 12. Here we divided both the numerator and the denominator of this expression by 6. In the numerator we have 6, so 6 over 6 is 1, so 6 will get cancelled. In the denominator we have in total 12, and 12 over 6 is 2, so we cancel 12, and instead of 12 we wrote down 2. So we actually found out that the radius of this circle that blocks the green triangle BCD equals to the square root of 61 times square root of 10 over 2. Okay, and according to the algebraic identity that the square root of A times square root of B equals to the square root of A times B, we can write down that the square root of 61 times square root of 10 equals to the square root of 61 times 10, all divided by 2. The 61 times 10 is 610. So in conclusion, we found out that the radius of this circle that blocks the green triangle BCD equals to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. We finished with the first method. Then I presented to you the second method. I will not repeat on the same thing that we have already done in the first method. So here, from point C, we draw perpendicular on AD. Therefore, this angle equals to 90 degrees, this angle equals to 90 degrees. We define the touching point of the perpendicular from point C on AD as E. So quadrilateral ABEC is 1, 2, 3 right angles. The fourth angle must be also equal to 90 degrees, and because of the fact that quadrilateral ECAB has 4 right angles, quadrilateral ABEC is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AB equals to EC, and AB equals to 6, therefore EC equals also to 6. According to the same rule, BC equals to AE, but BC equals to 13, therefore AE also equals to 13. What is the value of AD? AD equals to what is the value of ED? Here, ED equals to AD minus AE. AD equals to 18, AE equals to 13. AD minus AE is 18 minus 13, that is 5. So we found out that ED equals to 5 units. Then from the center of this circle, that is to say from point O, we drew perpendicular on chord BC. That is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and BC as capital N. Then I presented to you rule number 2, and we implemented rule number 2 in our drawing. According to rule number 2, if we have a circle, the center of the circle is at point O, and we have chord BC that could be any chord, and if from point O we will draw perpendicular on BC, that is to say this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction, we define the touching point of the perpendicular from point O and BC as E. Then the perpendicular OE on chord BC bisect BC, that is to say BE equals to EC. According to rule number 2, the perpendicular OE on chord BC bisect BC. That is to say, BE equals to EC. So we can implement rule number 2 in our drawing. Why? Because in our drawing we have perpendicular ON on chord BC. We have perpendicular ON on chord BC. And according to rule number 2, the perpendicular ON bisects chord BC. That is to say, BN equals to NC. So according to rule number 2, BN equals to NC. Then we focused on quadrilateral ABMN, the upper quadrilateral ABMN. In quadrilateral ABMN, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. And therefore, in quadrilateral ABMN, we have 4 right angles. Therefore, quadrilateral ABMN that has 4 right angles, it is the rectangle. Quadrilateral ABMN, because of the fact that it has 4 right angles, is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AM equals to BN. AM equals to BN. Likewise, we focus on quadrilateral MNEC. In quadrilateral MNEC, we have this angle equals to 90 degrees according to our construction. And then we have this angle equals to 90 degrees also according to our construction. And this angle, it is also equals to 90 degrees because of the fact that FD is chord. FD is a chord, it must be a straight line. And we know that the sum of the angles at the right side of the straight line FD must be equal to 180 degrees. So which angles we have in the right side of FD at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees. Therefore the missing angle must be equal to 90 degrees. So in conclusion, we found out that in quadrilateral MNEC we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. And because of the fact that in quadrilateral MNEC we have 4 right angles, therefore quadrilateral MNEC is a rectangle. Okay, here quadrilateral MNEC is a rectangle because of the fact that it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, ME equals to NC. ME equals to NC. So we can summarize what we have already found out. We have already found out that according to rule number 1, BN equals to NC. BN equals to NC according to rule number 2. This is rule number 2. But we have already found out that BN also equals to AM. So we can write here that BN equals to AM. And we have already found out that NC it is also equals to ME. Therefore we can write here that NC equals to ME. And from this long equation, AM equals to BN equals to NC equals to ME. We will derive that AM equals to ME. AM equals to ME. Okay, here AM, this is AM, that is equal to ME. Okay, in the next step we extend that line segment AD by a straight line until it touches the circle at point F. In this way we created chord FD. Okay, and we have from point O, we already drew perpendicular on BC. So here ON as perpendicular must be a straight line. If we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the upper side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees. Therefore, the missing angle must be also equal to 90 degrees in order to complete the sum of the angles and the upper side of ON at point M to 180 degrees. The missing angle here must be equal to 90 degrees. Likewise, we will focus on the lower side of the straight line ON at point M. We have here at the lower side of ON at point M, the sum of the angles must be equal to 180 degrees. Which angles we have at the lower side of ON at point M? We have this angle that is equal to 90 degrees. Plus the missing angle, in total, they must be equal to 180 degrees according to the rule that I mentioned. Therefore, the missing angle must be also equal to 90 degrees. So we found out that those two angles are both equal to 90 degrees. That is to say, line segment OM is perpendicular to chord FD. Okay? So we can write down that line segment OM that exists from the center of the circle is perpendicular to chord FD. Here OM is perpendicular to chord FD. That is to say, we can implement here rule number 2. Why? Because from the center of the circle we have perpendicular to chord FD. The perpendicular OM from the center of the circle bisects chord FD. That is to say, FM equals to MD. According to rule number 2, FM equals to MD. But what is the value of FM? FM equals to FA plus AM. So we can substitute FM by FA plus AM. What is the value of MD? The value of MD is ME plus ED. Here, MD equals to ME plus ED. So in conclusion, we found out that FA plus AM must be equal to ME plus ED. But because of the fact that we have already found out that AM equals to ME, here, AM equals to ME, that is to say, we can cancel AM and ME. Why? Because they are equal to each other. So we left only with FA that is equal to ED. Here, FA equal to ED. Here, line segment FA equals to ED. But we have already found out that ED equals to 5 units. FA equals to ED and ED equals to 5 units. So from this equation, FA equals to ED equals to 5, we will derive that FA is also equals to 5 units. Here, FA equals to 5 units. Okay? In the next step, I actually presented to you the old rule number 2. We implemented the old rule number 2 in our drawing. According to the old rule number 2, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can implement the old rule number 2 in our drawing. Why? Because in our drawing, we have chord FD that intersects with chord PB at point A. Repeat again, chord FD intersects with chord PB at point A. Point A is the intersection point of the two chords with each other. Therefore, we can implement here rule number 2. According to rule number 2, we will get that FA times AD equals to PA times AB. Repeat again, FA times AD equals to PA times AB. Okay, FA equals to 5 units, AD equals to 18 units, PA is the missing line segment, so we leave it as it is, and AB equals to 6 units. AB equals to 6 units. Okay, so in conclusion, we found out that 5 times 18 equals to PA times 6. We divided this equation by 6, and we found out that PA, the missing line segment PA, equals to 5 times 18 over 6. 18 over 6 is 3, and 3 times 5 is 15. So in conclusion, we found out that the missing line segment PA equals to 15 units in its length. So PA equals to 15. In the next step, I presented to you actually a new rule number 4. We implemented rule number 4 in our drawing. According to the new rule number 4, if chord AB intersects with chord CD at 90 degrees. That is to say, they created between them in the intersection point 90 degrees. Here, this angle equals to 90 degrees. And the intersection point occurs at point O. Then the following equation is true. Here, capital R is the radius of this circle. E is the center of the circle, M is the point of the circle itself, therefore EM is the radius of this circle that we define as capital R. So, if this is the reality that we have, then the following equation is true. That 4 times R squared, R is the radius of this circle, equals to AO squared plus OB squared plus CO squared plus OD squared. Okay, I repeat again. 4R squared, R is the radius of the circle, will be equal to AO squared plus OB squared plus CO squared plus OD squared. Actually, we can implement this rule number 4 in our drawing. Why? Because of the fact that in our drawing we have chord FD, this is chord FD that intersects with chord PB, this is chord PB at 90 degrees. They create between them in the intersection point, that is to say at point A, 90 degrees. That is to say, we can implement here rule number 4. Why? Because they create between them at the intersection point 90 degrees. And according, so here I repeat again, in our original drawing, chord FD intersects with chord PB at 90 degrees. It occurs at point A. Therefore, according to rule number 4, we'll get that 4R squared, R is the radius of this circle, will be equal to FA squared plus AD squared plus PA squared plus AB squared. Repeat again, 4R squared equals to FA squared plus AD squared plus PA squared plus AB squared. So for 4R squared equals to FA squared. FA equals to 5, therefore FA squared equals to 25 plus AD squared. Here AD equals to 18, so AD squared equals to 18 squared, that is 324, plus PA squared. PA equals to 15, so PA squared equals to 15 squared, that is 225, plus AB squared. AB equals to 6, so AB squared equals to 6 squared, that is 36. So in conclusion, we found out that 4R squared, according to rule number 4, equals to 25 plus 324 plus 225 plus 36. Here, 25 plus 225 is 250, and 324 plus 36 is 260. So in conclusion, we found out that 4R squared equals to 250 plus 360. 250 plus 360 is 610. So in conclusion, we found out that 4R squared equals to 610. We divided this equation by 4, and we found out that capital R squared equals to 610 over 4. We took a root out of this equation, and we found out that R equals to the square root of 610 over 4. That is to say, R equals to the square root of 610, and the square root of 4 is 2. So we took 4 out of the root. So in conclusion, we found out that the radius of this circle, the radius that we are looking for, it is equal to either the square root of 610 over 2 units, or in terms of numbers, it is equal to 12.349 units. Okay? Thank you very much.